Hey, how's it going, everyone? I decided to make a video for my AP Statistics students here. How do I find and interpret a confidence interval? So the purpose of a confidence interval is, given a random sample from a large population, what is a range of values for which it is reasonable to believe that the parameter falls between? Or in other words, if you were to ask a question such as, how many people support a political opinion? How many of your customers are satisfied? How many rares will I get if I open 100 loot boxes? I'm going to go from that example, actually. Your favorite Twitch streamer opened 100 loot boxes on stream and got 10 rares. If you opened up 100 boxes, what is a range of rares you should expect to get? That is, if you got fewer than 7, should you be angry? If you got 15, are you insanely lucky? Turns out the answer to both of these questions is no. You should not be angry if you got fewer than 7. And if you got 15, that's actually also an expected number. Let's check out exactly how we can do the math behind it. First of all, for the AP statistics test, in order to do any of these questions, you first need to decide what situation you are in. The situation that we are in here is going to be one that uses what is called a sample proportion. So we are finding the confidence interval for a sample proportion. And that is exactly what we are doing in this case. Now, how did you know that it's a sample proportion? The reason why we knew it was a sample proportion is because we were in a binary situation. That is to say, you're going to be doing a sample proportion anytime you're in a binary situation, meaning that you can either get a rare, you either get a rare or you don't. Get a rare or you do not, or not. Those are the only two situations. And you are interested in a specific proportion, specifically the number of rares divided by the total boxes opened. Total opened. Man, that's the word opened. What can you do? All right, so it's the number of rares over the total opened, and we are going to give this thing a name of p hat. Now, for the first part of this, we are simply going to show what the formula is. We're going to do the formula, and we're not really going to worry about where things come from. We're going to be doing it the quote unquote old school way, the way that you could do it with a 4-function calculator in the table of values in the back of your book and the formula sheet. And then afterwards, we'll go ahead and use a calculator for it. However, in order to find a confidence interval for a sample proportion, you must have 3 checks to make sure that you are even able to do inference in the first place. So we're going to go ahead and do 3 checks to figure out this situation. So every single different type of confidence interval will have its own rules for which checks you do. For the sample proportion, we're going to do 3 checks. The 3 checks are very straightforward. Number 1 is called the normality condition. The normality condition for a confidence interval, you are going to be checking to see if p hat multiplied by n is greater than or equal to 10, and if 1 minus p hat times n is greater than or equal to 10. And in this case, p hat times n is simply going to be the raw number of rares, because n is the total opened. So that is your n right there, your total open. Maybe I should have written that there. And up there, your number of rares. In this case, if we were just to do our number of rares over total opened times n, we would in fact get 10, and 1 minus that proportion is the number of failures, the not rares. In this case, it would have been 90. So in this case, we are good to go. Our normality condition is met because the p hat times n is in fact equal to 10, and 1 minus p hat times n is equal to 90. So the normality condition is met. The second condition for inference that we need to do is to check to see if your sample comes from a large enough population. And this is the independence check. Independence check. I need to take a drink of water. I'm going to pause really quick. So for the independence check, what you're going to end up doing is checking to see if your sample size is less than 1/10 of the population. So you need to check to see if n is less than or equal to 1/10 of the entire population. It is usually easier to not think about fractions and instead answer the question, is 10 times the sample size less than or equal to the population? That is an easier question to answer. And in this case, we're opening up loot boxes. In theory, if you had millions and millions of dollars, you could just open up loot boxes forever and ever and ever and ever. So because of this, we can very clearly see that the 10 times our sample size of 100 is definitely less than or equal to our large population. So we can just say n is very large. And therefore we are good to go for our independence check. And our very last one, we have to have a randomness check. This is actually going to be part of almost every single situation. These are the three you're going to be checking for a lot: normality, independence, and random. But in this case, we have to assume that these loot boxes are in fact random. Assumed random. We're assuming that they are not cheating us with these loot boxes. And we're also assuming that there's not some sort of like pity system where it's like, oh no, you didn't open a rare in the first 15 and therefore we're going to give you a free rare. So these are like truly random. I mean, that's part of the independence as well, that there's no dependent events going on. Anyways, once you have checked for your 3 different conditions, you're now going to apply a formula. In general, your formula for your confidence interval is always going to be the statistic or the sample. So you're going to take your sample of some kind, whatever it is, your sample statistic plus or minus the margin of error and for for all these situations in general, this margin of error here, we are going to use the letters ME for it. It is almost always going to be a critical value. So we're going to say critical value, critical times the standard deviation divided by the square root of n. This is a generalized formula for what that margin of error is going to be. For this particular problem, our formula is going to be p hat plus or minus z star times the square root of p hat times 1 minus p hat divided by n. So p hat, that is your sample statistic. It is the number of rares out of the total opened. In this case, we had our streamer got 10 rares out of 100 opened. And we now need to add plus or minus z star. Now, what's z star? Z star is actually the level of confidence for which you wish to have. That is to say, you're taking this reasonable belief, and because you don't know what the actual percentages are here, you have to say, well, I am a certain amount confident. If you say something like that you're 50% confident, then you're really not confident at all. And, anything could be true. If you take something like 75% confident, if you're somebody who's saying they're 75% confident in the truth of something, how much do you actually believe them? And for most of this stuff, we're going to end up using 95% confidence. In order to find your Z star, you have really only 2 different options for Z star on the AP Stats test. You can either A, use your calculator, or B, use the table of values. I'm first going to find the value using the table of values in the back of this formula sheet here. And then we're also going to show where you could find that Z star on the calculator. So I'm going to go to a new page really quick, find Z star, and then go back to a new one. So we have to go to a new page to figure out this Z star idea, this critical value. So let's go ahead and do that. Let's find our critical value. So find finding Z star. So to find Z star, you first need to figure out what your confidence level is. So step number one is, what is your confidence level? For the purposes of this video, I'm going to go ahead and say that my confidence level is at 95%. Common confidence intervals that you'll end up on the AP test are going to be 90%, 95, 98, and 99. However, they occasionally throw you for a loop where they do like a random like 92% confidence so that you can't just like memorize a number, and you actually have to go through the motions of figuring out what this is. So you figure out what your confidence level is. After you figure out what your confidence level is, you then figure out, then you find the Z-score that is the middle confidence percentage amount. So the middle 95%, that is the middle 95% of the distribution, of the normal distribution. So really what you're doing when you're doing this whole process is you're saying, hey, I've got a normal distribution and I would like to know where the middle 95% of the values are, remembering that this distance here is going to be, that one standard deviation out to that first inflection point. This is going to be, negative that one standard deviation over here. And we are asking what number is going to make it so that we are at 95% is filled in here, that we have 95%, that this purple here is 95% of the data. Because we are trying to figure that out, in order to actually use our table in the back of the book, or to use our calculator for that matter, we are going to have to ask ourselves a slightly different question. That is to say, we're going to instead say, well, this number here that gives us 2.5%, what is it? And the reason why it's 2.5% is because there's also 2.5% on this side, and 2.5 plus 2.5 is 5, and that is your 95%. So what you're really doing is you're finding out Z of, and you're doing 100 minus your confidence percentage, and you are dividing it by 2. So you're figuring out where that is in this case. So in this problem, we're doing 100 minus 95 over 2. And that's going to give us that 5 over 2, which is our 2.5%. So we're going to find this 2.5% idea, and remembering that 2.5% is equal to 0.025. So now we're going to be taking our AP statistics formula sheets, our standard table of probabilities, and we are looking for what point in time do we end up with 2.5% of the data. So looking over here, it's going to be smaller than any of these numbers. So where are we even going for this? Is there a backside over here that has a better set of numbers? You gotta be more on top of this here, Mr. Richards, finding out your data right away. This is silliness right now. You're not being very professional. We want to have a value. Where are we? We want 2.5. It only goes to 0.08. Only goes to 0.06. What am I supposed to do? Maybe there's I can go to 97.5%. That's what we'll do. We'll go to 97.5%. Okay, so we found a 1.9 is our 97.5%. That's the, the other side, the 2.5% I found earlier. So we have 1.9, and we scroll all the way to the top, and we get 0.06. Or in other words, we end up with a Z-score. A Z-star is equal to 1.96. So that is effectively what you are doing. Now, if you don't want to use the table, you still have to go through all of these motions to figure out what the Z-star is. You still need to figure out this 0.025, but instead, we're going to be using the inverse norm feature of the calculator. So from this number is either the table or the inverse norm of the calculator. So table or inverse norm. So table or inverse norm. And in this case, to find the inverse norm on your TI 83, so you're going to go, or 84, sorry, I don't know where that came from. So you're going to go second vars. So we hit the second button and then the vars button to get the distributions. Inverse norm is number 3, and we are doing an area that is 0.025. You do not need anything else changed. If you don't have this left, center, right, don't worry about it. Yours are going to be just left, and you can go ahead and figure out that is negative 1.96. Sure enough, that same exact value we just found. It doesn't matter whether it's plus or minus because we're going to be adding and subtracting it. Please note, if you do have this updated calculator or maybe a different calculator that has it, you could have just done the area of 0.95 and went to the center, and that also would have found it for you. It would have found this this 1.96 on both sides of the equation for you. Regardless, for this problem, we have found our z star is 1.96. Now we can go back to our original problem. So we found our z star using our calculator there. So we're going to go ahead and fill in our z star now of 1.96. And we're going to be multiplying this by that same exact sample proportion. So our sample proportion here was our rares over total opened. It was that 10 over 100. So we have 10 over 100 multiplied by the 1 minus that sample proportion, the rares that we didn't get. So 90 over 100, and that's all being divided by another 100 there. Now, I chose the numbers 100 there because it's going to be easier for us to do square roots if we wanted to be able to. However, ultimately, once you've gotten to this step, you can definitely just start plugging things into your calculator. So I'm just going to go ahead and do not as much on the calculator, though. We're going to get 0.10 plus or minus 1.96 times. And just to make my life easier plugging this into the calculator, we're going to write this as 0.1 times 0.9. And then the square root of 100 is 10. So all divided by 10. And that's what I'm going to type into my calculator because that's a lot easier to type in. So just doing it all here, we're going to go ahead and do 0.10 plus 1.96 times our fraction button, a square root for the top of 0.1 times 0.9. And on the bottom, we have 10. And we end up with 0.1588 as the right-hand side. So our chance of getting a rare is our rare chance here. Rare chance is on the upper end 15.88%, and our rare chance on the lower end would be just changing this to a negative sign. So if we change this thing to a negative sign, we'll get that 4.12%. And therefore, we can come to our conclusion, our sentence we're going to write for interpreting. We can say we are 95% confident we will get, and I think it's appropriate here to round because we are talking about a whole number, a number of rares. So I think it's very, it's totally fine to round in a situation like this, especially when the numbers are so close. And we've already made some normality assumptions anyways. So slightly increasing the size of our interval is fine. Please note, you don't want to decrease the size of your interval. So when you decrease the size of the interval, it would not be the best, but we're going to go say we are 95% confident we will get between 4 and 16 rares. And that is out of 100 boxes. I can't, I'm out of room here, out of 100 boxes. And therefore, our original question that we are going back to is, if you got fewer than 7, should you be angry? And the answer is no. You can only really be angry if you got fewer than 4. And likewise, you can only say that you are truly a lucky person if you got over 16. So you have to get at least 17 rares before you can consider yourself a very, very lucky person out of this entire situation. Now, please note, I did not show that this entire part here is actually technically optional. Once you've written this formula down and you've written down your Z-star, you don't need to do the whole formula. What you can do instead is use the stat button on your calculator to do all the work for you. So you hit the stat button and you scroll to the word test. And now we're going to go find the one proportion Z interval, letter A. And in this problem, we had 10 rares is what we got. We had 100 was our total, and our confidence level is 95%. And we can just go ahead and hit calculate. And sure enough, we get those same exact 4.12% numbers and 15.8 without doing any of this extra thought process. We just did the work right away. And you're allowed to do that on the AP exam. You can just use this. You don't got to plug all this stuff in like crazy. You can just use that. You do need to do your conditions for inference here, your checks for inference. You do need to be able to write that you're 95% confident. We will get 14 and 16 rares in 100 loot boxes. I hope this was an informative video. Have a wonderful rest of your day.